Hello everyone. Today we are into the top topic of the first chapter, that is electric flux. First of all, to know electric flux, we need to know about area vector. Generally, we know that area is a scalar quantity, but in that area, if you give a particular direction, that area will be termed as area vector. Suppose, say this is the surface of this is the surface where the charges are distributed. Now suppose this is S, let me write, this is the surface. If I choose a small area element, say ds, and if I give a direction normal to it and kept, then this area will be called as area vector. You will have to know this board is two-dimensional, so you see that the arrow is going upside. But if this is the surface, the board is the surface, then the area vector is pointing like this, perpendicular to the surface. Suppose if this is the surface, if I choose an area element here, then the area vector will be pointing perpendicular to it like this. If I choose the area here, then it will be perpendicular, the direction of area vector will be perpendicular to the surface like this. So an area with a direction, we call it as area vector, and you must be pretty sure that the direction is perpendicular to the surface. Now let us see about this electric flux. Electric flux linked with any surface wherever charges are distributed, linked with any surface, it is defined as the total number of electric field lines that passes normally through that surface. Normally means perpendicular through that surface. If you have a bundle of electric field lines passing like this, many field lines passing like this, then if it is passing then through a particular surface, then that bundle of the number of field lines, total number of field lines that is passing through the surface, we call it as electric flux. Suppose if d phi is the electric flux that is passing over a surface, say this is the surface S, and choosing one small area element ds, area vector will be pointing normally perpendicular to the surface, and if this is the direction of electric field lines, then making an angle theta with it, then electric flux d phi passing through this surface ds, surface element ds, will be given by d phi is equal to E dot ds. E dot ds, if you write in scalar form, it will be E ds cos theta. Then the total number of electric field lines is the total flux to find out. We'll integrate this d phi. If you integrate d phi, you will get phi. Surface integration for the whole surface as sum of all like this ds covering the whole surface. So sum we are doing d phi, and this one will be written as d phi. It is E ds cos theta. This will represent the total flux or total number of field lines passing through the whole surface that you can see here. Now there are three special cases. Case 1, when theta lies between 0 degree and 90 degree, it can be equal to 0 but cannot be equal to 90 degree, then the electric flux, you can write as phi E also here, is positive. The second case, when theta is equal to exactly 90 degree, then electric flux will be 0. Total electric flux will be 0. And when theta lies between 90 degree to 180 degree, it cannot be equal to 90 degree but can be equal to 180 degree, then phi E will be negative. Here positive means the surface will enclose a net positive charge. 0 means the surface does not have any charge, and negative indicates the surface is enclosing a net negative charge. That is the meaning, because cos value 90 to 180 is all negative. Cos 90 degree is 0 and cos values from 0 to 90 degree are all positive. So that gives us an idea about whether the surface will be carrying positive charge or it will carry negative charge or it will not carry any charge. Now let us come to a very important theorem, or law also we say. Gauss theorem. Gauss theorem, many people they think, for what reason do we do Gauss theorem? But you have to remember and keep in mind that Gauss theorem is particularly done to find out the electric field intensity. Earlier also we have discussed how to find out electric field intensity with the help of Coulomb's law. But this Gauss theorem gives us an easy way to measure the electric field intensity. So the theorem says like this: the surface integration or the surface integral of electric field intensity, like this, surface integral of the electric field intensity, or this one, as we have learned, this is called the flux, the electric flux. This is the surface integral of the electric field intensity is equal to 1 by epsilon naught, the net charge, 1 by epsilon naught times the net charge enclosed by the surface. So it is a mathematical relation to find out the electric field intensity. Let us prove this Gauss theorem and see. For proving Gauss theorem, we generally take a positive charge, and as we know the field lines, it goes away from the positive charge in all the directions. Like in the previous classes we have discussed, it goes radially outward, like this, like this, like this, like this, like this. So here you have to take it that way. The field line is growing like this, it is going away, and an equal distance at each point. These are the points which are at an equal distance from the positive charge. Suppose this place that O. If I take a boundary like this, then a sphere will be formed. One sphere is formed. The board is appearing like a circle, but let's think that a sphere is formed. All these points are at an equal distance from the positive charge. Now, this is called your Gaussian surface. This is called your Gaussian surface. You have to keep one thing in mind. Gaussian surface is an imaginary surface. It is an imaginary surface. Now at this Gaussian surface, I want to find out the electric field intensity in a small region of the surface. Let me say it as ds. This is your S, the whole surface. A small region I am taking, this is ds. Then now, if I draw area vector there, the direction of area vector, it will be pointing perpendicular like this, ds, or we write as n cap ds. This is the direction of area vector. And when we talk about the direction of electric field line, then the electric field line also goes radially. It goes along the same direction. It's coming from here, it's going in the same direction. So angle between E and ds, here it is purely 0 degree. It is not necessary that you have to choose this area element here. You can choose here, you can choose here. The same thing you will get. Electric field line will come like this. Area vector will also be along with it. The angle between E and ds will be always 0. It is a symmetric surface. Gaussian surface must be a symmetric surface. Now, if you think that the radius of this Gaussian surface is small letter r, you can do this way also. If this is r, here also it will be r, or anywhere you draw it will be r. The electric flux, if you find out now, electric flux through the surface ds is d phi e is equal to E dot ds. Electric field intensity, it is 1 by 4 pi epsilon naught. Charge divided by distance here is r. The charge is positive charge here. Q divided by r square dot r cap in terms of vector dot ds is n cap ds. So this one can be written as 1 by 4 pi epsilon naught q by r square ds. In the bracket you can write unit vectors r cap dot n cap. This one can be written as d phi e is equal to 1 by 4 pi epsilon naught q divided by r square ds. And both are unit vectors. The dot product of two unit vector is always 1, since r cap dot n cap is equal to 1. So now this total electric flux, if you want to find out for the whole surface, therefore phi, we will integrate this 1 by 4 pi epsilon naught q divided by r square integration and the closed surface ds. Now 1 by 4 pi epsilon naught q divided by r square integration, sum of all the area, the surface area of the sphere is 4 pi r square. That is the surface area of sphere. And if you cancel it, 4 pi and r square, you get 1 by epsilon naught the net charge q. So this proves Gauss theorem. Again, as I said earlier, if phi is positive, then the net charge enclosed by the surface will be considered as positively charged. If the surface encloses net negative charge, then phi value will be negative. And if it does not enclose any charge, then phi value will be equal to 0. So this will decide positive, negative or 0. Thank you and have a nice day.